This is one of those points where we are going to see linear algebra and calculus come together. And we're going to look at three specific types of vectors and or matrices called the gradient vector, Jacobian, and the Hessian, or Hessian if you prefer. So what are these things? Well, the gradient vector is a vector pertaining to a function. And it is written like this. Some people will just say grad f or gradient f is a 1/2 vector containing each partial derivative respectively. So in other words, we have x and we have y. We just want to keep the order the same. So inside of our vector, we're going to have the partial of f with respect to x, and then the partial of f with respect to y. So it's going to look like this. The gradient of f in our case, generically, and you can just say of f, you don't have to say xy, but I'm just being explicit here. It will look like this. It'll have f sub x, and then as a separate entry, it'll have f sub y, and it has one row by two columns. So we have the two columns here, and then we have the one row here. So first we need to just compute those partial derivatives. F sub x will be 2x, derivative of the first term. Y is held constant, so we have 3yx, and 3y is a constant. The derivative of a constant times x is just the constant. So there's our partial with respect to x. So we could begin writing this. We could say, well, in the first entry, we're going to have 2x plus 3y. There's our f sub x, and our f sub y will be 0 plus 3x is a constant. Derivative of constant y is just the constant. And so our second component in here will be the function 3x. So our partial with respect to x, our partial with respect to y. Now, in general, we may have more than just the two variables. We may have n of them. And the best way to write this out is instead of having, letters, distinct letters for each of the variables, we usually just subscript the, because we may have more than 26, which is beyond our alphabet. And so it just makes sense to use numerical subscripts to denote the variables, since we'll never run out of those. And so in the case of having n variables, notice there are n variables here, still just one output, which we may prefer to call z or just f of those input variables. The output is single output, but we have n separate variables, so this is going to be a 1/n vector. So it'll look like this. The gradient of f would just have the partial with respect to the first variable, f sub x1, and then the next entry would be f sub x2, and then f sub x3. So these are just the partial derivatives with respect to each of the variables. And because we don't know exactly how big n is going to be, we'll have one column entry for each of those partial derivatives. And usually that's the way we write it. So if we had x1, x2, x3, then we would have three distinct derivatives in here. Just as a quick example, let's say we had f of x1, x2, x3. And let's just say the function was relatively simple, a linear one. We had 2x1 plus 3x2 plus 9x3. Well, then our partials, and I'm just going to kind of do this intuitively, the derivative with respect to x1, well, these other two would be 0 since all of the other variables are being held constant. And the derivative of this would just be 2. And then the derivative with respect to x2 would be just 3. And the derivative with respect to x3 would be 9. So we would have this 1/3 vector of derivatives. Now, here is the really valuable part of the gradient vector. Why do we use this? Well, the gradient vector at a given point, let's just denote that point x naught, y naught. Remember, x and y are variables. X and y are on a spectrum of values, and x naught, y naught just says we're specifying a specific instance of x and y, and it points in the direction of maximal rate of change of f. That is assuming that the gradient is not just the zero vector. If it's the zero vector, then it doesn't matter which direction you point in, it's going to be the zero vector. And we'll take a look at this in just a moment. That is, this is the vector indicating where we should travel along the surface in order to increase the output most rapidly. That's a huge benefit, as we'll see later on when we think about things like gradient descent. Also a consequence of this, if the gradient vector points in the direction of maximal ascent, then the opposite of that should therefore point in the direction of maximal descent. Opposite just means that we change the signs of both of the components. Now I'll show you as an example to give you some intuition about this. The paraboloid x squared plus y squared. Its gradient vector would be derivative with respect to x, which would be 2x. Derivative with respect to y would be 2y. Now let's say we specified a point on this surface. So here I'm just going to look at the point 1, 1, which will be, the point shooting straight up right about there. We'll just say that's the point 1, 1. Okay, so we're looking at the point 1, 1. There's our x naught and our y naught. And at that point, we could of course compute the output of the surface. F of 1, 1 would just be 1 squared plus 1 squared is 2. So this would actually be the ordered triple 1, 1, 2. Okay, and now we want to know at that point what is the rate of change. Well, the gradient of f at the point 1, 1 would be 2 times 1 is 2, 2 times 1 is 2. So that's a vector that has a change in the x direction of 2 units, a change in the y direction of 2 units. So where would we travel? Well, it's kind of hard to visualize, right, without rotating this thing and really getting a sense. But basically, this would say increase x by 2, increase y by 2. So we would be heading up, somewhere in this direction. And hopefully, just from an intuitive sense, you at least see that we're moving up the surface as opposed to down the surface. Now, if that's the gradient, then if we moved in the direction -2, -2, well, that would be precisely down in the opposite direction, and that would move us in the direction of the minimum. And you could pick other points, like if you look at the gradient of f at 0, 0, well, that's precisely going to be the 0 vector. And of course, when you're at the bottom of the surface, it doesn't really matter where you move because you're talking about the plane. The tangent plane would just be the plane f of xy equals 0. And so the tangent plane doesn't matter which direction you move in when you're at the minimum, you're going to have 0 change in all directions. So that's where the exception is to this rule that the gradient points in the direction of maximal rate of change. So this could be helpful in the sense that if we're trying to maximize something, then, and we're at a specific point and we want to know where should we move, well, as long as we always move in the direction of the gradient vector, and then of course we need to recompute. So think about this as we could travel ourselves up to the maximum by computing the gradient at the point, moving an infinitesimally small amount into the direction of that gradient, then recomputing the gradient at that new point, and then again moving in an infinitesimally small amount of change in that new direction. We kind of repeat this process. We'll eventually whittle our way to a maximum if it has one. Alternatively, if we move in the opposite direction and then recompute, we'll eventually move ourselves in the direction of the minimum. Now, this is provable, but without some more details of working with multivariable functions, such as thinking about what we call contours. And it has a lot to do with contours, which basically, if at every single value of z we sliced this thing with the horizontal plane, we would get a circular contour ring, and then we could repeat that, and as we would move our z value down, those contour rings would get smaller and smaller, as you can see, because the bowl shape gets narrower as we move our way towards z equals 0. Now, we also have what's called the Jacobian matrix, and the Jacobian matrix is similar to the gradient vector, except suppose you have multiple functions. In this case, we have a function f and another function g, both of which are functions of the same variables, right? Same variable set. Then basically we would have as its rows, we would have the gradients of each of these specific functions. So notice that we have a gradient of f and the gradient of g. So that's an easy way to think about it. If you have multiple functions, you just compute the gradient of each of those functions and then stack them as rows. So here in this case, if we have x squared plus 3xy as f, I guess we need a g. Now we already have the gradients of both of these functions. We determined that the gradient of f is the vector 2x and the vector 3y. Excuse me, 2x and 3x. Right? Did we do that correctly up here? I'm sorry, 2x plus 3y, and then 3x. Okay, 2x plus 3y and 3x. Just doubting myself there for a moment. And then the gradient of g we just determined. This is the same function. We called it f a moment ago, but we'll call it g now. This is going to be 2x and 2y. And so we just said that the Jacobian is going to have, as its two rows, it'll have the gradient of f and it'll have the gradient of g. And so that's going to be the matrix 2x plus 3y and 3x as the first row components. And then the second row will again have two entries, 2x and 2y. And so notice this will be a 2 by 2 matrix. In general, you may have more functions than f and g, and you may have more variables than just x and y. So let's denote the functions f2 all the way up to fm. So we have m functions and then n variables, which again we'll just denote x1, x2 all the way up to x sub n. So m and n may be different, right? We may have 30 functions and 8 variables, in which case we would have 30 rows and 8 columns, because remember each column, like up here, each column corresponds to the partials with respect to x, and then these correspond to the partials with respect to y of those functions. So each row, here we have f1, f2, all the way down to fm. And then along the columns, we would have x1, and then the next column would be x2. We didn't show it here, but that's what would be here. And then all the way up to xn. So basically, each of these is just a gradient of its respective function. You can see this can get pretty big. And the function, the Jacobian has many applications. We won't quite explore those here yet, but there are some things involving the determinant that would come in handy when we're talking about the Jacobian. We'll look at one more matrix, and this is called the Hessian matrix, or the Hessian matrix if you prefer, and it really just contains the second order partial derivatives of a given function, of a single function. And so in the top left and the bottom right, notice that those are going to be with respect to x and y, and then along the diagonals we're going to have the mixed partial fxy and fyx. Now since these are the same, this matrix will be symmetric. And all that means is that if you look at H and you look at H transpose, they will be the same. So remember what H transpose does is it basically takes each of the columns and turns them into rows. So if H is, as we have here, fxx, fyx, fxy, and fyy, if you take these two columns and turn them into rows, then you get H transpose. So make this the first row, fxx and fyx. Okay, so that first column just became the first row. That's the definition of a transpose. This is transpose of H. And take the second column, make it the second row, fxy and fyy. Well, what we mean by they're symmetric is they're the same, right? They are exactly the same, and that makes sense because the top left and the bottom right components are still the same, but now the diagonals have switched. But since fyx and fxy are the same, well, then we haven't changed the diagonal entries, and so we call this a symmetric matrix. Okay, let's find the Hessian of one matrix here. So we already have that fx is 2x plus 3y. Fy is 3x. So let's go ahead and take the derivative of fx with respect to x, which will just give us 2. And now let's take fxy, which is the derivative with respect to y, which will give us 3. For fy, let's compute the derivative of that with respect to y, which is just 0. And let's compute the derivative with respect to x, which is 3. Okay, so that the Hessian has as its, and notice again, these are the same, and we've learned that the mixed partials will always be the same. So this will explain why it's symmetric, right? And so now we have at the top fxx, the bottom we have fx or fyy, and then here technically we have fxy, which is the same as fyx. And notice that if you transpose this, you take the first column and turn it into the first row, you get 2, 3. If you take the second column and make it into the second row, you get 3, 0. And notice that H is equal to H transpose. And that's where we're talking about symmetry. All right, we're pretty much done here with this. Notice something interesting about the Hessian. If you take the determinant of H, which remember the determinant of a matrix that has components little a, little b, little c, little d, is AD minus BC. That's the determinant of A, okay, which we would just write as the determinant of this matrix would be the product of the diagonals minus the product of the off diagonal. And if you take that of the Hessian matrix, the determinant of the Hessian matrix, well, you get the products of the diagonals. The Hessian, remember, along the diagonals has fxx and fyy. Fxx times fyy minus the product of the off diagonals, which would be the product of these two. And I'll just write fxy times fyx. Now, since these are the same, they are equal to each other, I can just write it as minus fxy squared. Or you could write it as fyx squared. It doesn't matter because they're both the same. And this is precisely what we referred to as the d value, or the d expression, when we're determining local minima or local maxima. So we would compute this thing at our point that we're questioning, at our critical point, and we would plug in that critical point's x and y values. And if this thing was less than 0 or bigger than 0, then we had to run the test and determine whether it was, according to the test, a local min, local max, saddle point, or potentially inconclusive. So that's an interesting feature of the Hessian matrix.